All right, good day. This is AP Calculus. I'm Mr. McCully. This is my presentation for section 5.3. So let's jump right into it. This is really one of the easier sections, but there's a lot of review stuff, so I want to make sure that I get over it. I hope I can get it done in under 22 minutes or 25 minutes. Let's see what we've got. So today we're going to talk about inverse functions and how they work in the context of derivatives. We're going to determine if a function has an inverse and how to find it, and then we are going to find the derivative of an inverse function. So a little bit of review stuff. Definition of inverse. A function g is the inverse of a function f if, when you compose the function f with g, and then reduce it, the result is x for any x in the domain of g. And then if you compose it the other way, where you have g composed with f of x, then that result after you've reduced everything is x for each of the values x in the domain of f. Remember that the function g is denoted by f inverse, and that's how we read it. Graphically, the inverse of any function is a reflection about the line y equals x, so a diagonal line. And a function has an inverse if and only if it's one-to-one. And continuity and differentiability rules of inverse functions, you can find those on page 347. I think I go over a couple of those as we go further on. So the function has an inverse if and only if it's one-to-one. And if f is strictly monotonic on its entire domain, then it is one-to-one and therefore has an inverse function. So let's talk about what that actually means. So if I throw out a graph here and we talk about two functions, and we'll do them in different colors. So I've got this function here, which we'll call f of x, and this function here, which we will call g of x. So we'll call this g of x, green for g. All right, so this function, both of these are functions because they pass vertical line tests. So if I take that vertical line and I run it across there, I only cross that vertical line at one place anywhere in the domain of this function f of x. So it passes a vertical line test. Now, the function f does not pass a horizontal line test. And so at this point, you can see that it's crossing the horizontal line at three separate places. That means it's not one-to-one. And what do we mean by this thing, excuse me, one-to-one? What we mean there is for every 1x, there is 1y, and for every 1y, there is 1x. Now, the green function here, this function, no matter where we move our horizontal line and our vertical line, it only crosses that vertical or horizontal line one time. So that it means any time that you pick one x value, say x1, there is only one corresponding y value. So if we go like that, those things match up. Whereas if I pick say a single x value here, which I'll call x2, we can see that this y2 also corresponds to another point x3. So the red line, the red curve, is not a one-to-one function, whereas the green curve is one-to-one. So moving on. And finally, as far as new information goes, the derivative of an inverse function. If f is a function that is differentiable on some given interval, and if f has an inverse function called g, then g is differentiable for any value of x for which f, the first derivative of f of the g function is not equal to 0. That should be not equal to 0 there. So you may have to change that on the notes that I have there. And so, moreover, that g, that inverse function, the derivative of that inverse, is 1 over that first derivative of the composition of g, of f with g. And again, we need to have this because if this expression is equal to 0, this is undefined, UDF. So that's a real quick review of the review stuff. This is what we talked about last year, a little, and then this is the new stuff for this particular section. So just going over a few quick examples. If you have your book, I'm looking on page 349. We're talking number 4, and they want us to show that those two things are inverses of each other, and they say that the first function f of x is equal to 1 minus x to the third, and then g of x is equal to the third root of 1 minus x. So first thing I want to know, are these two functions one-to-one? Well, if you're not sure, you can always go to your graphic calculator. But just to kind of give you an idea, we know a lot about this graph. We know that it is a third-degree polynomial, so its end behavior is opposite, and since the leading coefficient is negative, it's up to the left and down to the right. Since we don't have a whole lot of terms, we're not going to have a whole lot of ups and downs near the origin, and we know we have a y-intercept of 1, so we know we've got something that probably looks like that. And then this one will be the inverse of that, and again, there's not a whole lot going on inside there, so we're not going to have a whole lot of curves. And if you want to take the time to investigate that a little bit better, you'll see it, but I'm just trying to keep things moving. So how do I show that they're inverses of each other? Well, we go through this whole process of doing the composition of f with g and g with f. So the first thing I want to do is I want to compose f with g of x, and then I'm going to come over here, I'm going to compose g with f of x. Now, just kind of off to the side, try and do a little bit of review here. What does that mean? Well, if I just said find f of 3, none of us would have any problem. We just go, it would be 1 minus, we plug in 3 for x to the third power, and we'd calculate that. That would be negative 27, so 1 minus 27 is negative 26. But when we, excuse me, when we compose a function with another function, instead of plugging in the number, we're going to plug in this entire expression. So we have f of, and I don't like that. Let's go back to my line. There we go. We have f of not g, but the expression for g. So the third root of 1 minus x. And that's equal to that one. And so the function f is 1 minus whatever you're plugging in to the third power. So this becomes 1 minus the parenthesis third root of 1 minus x to the third. Now remember, third root and third cancel out. So I've got 1 minus, basically 1 minus this entire quantity. I think I have a mistake. Nope, I don't. Let's see, how am I going to get, oh, okay, it's not a problem. I distribute my negatives. It's a dumb moment for Mr. McCulley there. So I distribute the negative 1, so I got 1 minus 1 plus x. These cancel, and I'm left with just x, and that's what we needed to do. Compose f with g, reduces down to x. And so doing the same thing over here, I've got g. I replace the innermost portion with this expression, so it's 1 minus x to the third. And then now g is take whatever you're plugging in and put it in for x there. So this thing becomes the third root of 1 minus the quantity 1 minus x to the third. All right, so simplifying. Again, you distribute the negative, so I've got the third root of 1 minus 1 plus x to the third. Those cancel. I've got the third root of x to the third, which is just x. So f and g are inverses. All right. moving on. All right, I move on to the next next section there. I'm looking at not, I don't want to look at 28, it looks 26. I meant to change that to 28 there. This one looks a little bit different, and I want to talk about the domain limit that they have with it. So number 28, they say f of x is equal to x squared, and then they put this little comma, and then they go x is greater than or equal to 0. Now, excuse me, they ask us to find the inverse of this particular function. Now, on a normal x squared function, and just real quick, and I'm not even going to get a graph out, we'll just throw something up there. In a normal x squared function, we know that it's going to look something like this. And that is obviously not one-to-one. If I do a vertical line test, it is a function. I do a horizontal line test, we see obviously not one-to-one. So what this thing does is it limits the domain so that the function f of x is 1-to-1. All right, and what that essentially does is it says it's only this function is true only for values of x that are greater than or equal to 0. So basically, all it's doing is it's erasing that portion right there, and now this function is 1-to-1. So going through the way that we normally find inverse functions, we take the x and the y and we switch them. So I'm gonna we'll do it. I got y equals x squared. Switch my x and y. And then I'm going to solve for y. So I'm going to take the square root of both sides, and remembering whenever I do the plus or minus, or whenever I take the square root, I add plus or minus, these cancel, get y equals plus or minus square root of x. Now, that's the graph of this thing. It essentially looks like this, because we have both the positive square root of x, which would be that, and the negative square root of x, which would be this bottom portion. But remember, it's a reflection of the line y, the inverses of the reflection of the line y equals x. So this portion and this portion are the values that we need, and we're going to get rid of the bottom portion and just say it's y equals square root of x. And then what we're getting rid of, as far as the graph goes, is we're getting rid of this bottom portion right here, and that is going to be our solution. All right, moving on to the next one, number 38. Now in number 38, excuse me, the reason I do ones like this is because there's a lot of questions on the AP Calc test where they just give you a graph and ask you to manipulate it. So in this one, they give us a graph where they plot a point. So I'm going to call this x, we'll call this y, and we'll go 1, 2, 3, we'll call that 4, we'll call that 8, do the same thing here. And right there, so 4 and 8. And so they give me a graph where I have one point that is at 0, 4, and then another point here at 2, 2, and then another point here at 4 or 6, 0. So let's connect the dots. And so the question asked me, first thing it says is, the first thing that we should do is make a table of values for the given point. So I want to do that first. And so this is my function f of x. So x and f of x, I have 0, 4, and then I have 2, 2, and then I have 6, 0. Now, they want us to find a table of values for what we're going to have as x. I don't like that. Let's make it a little bit better. And there we go. Get x and f inverse of x. So what will those points look like? Well, we go back to this original one. Remember, what did we do? We switched x and y. And that's literally what we're going to do here. We're just going to say in my f inverse function, I'm going to have 4, 0. I'm still going to have 2, 2, but I'm going to have 0, 6. So I took my x and my y's and I switched them. And so if I'm graphing that, I've got 0, 6, I still have 2, 2, and I have now 4, 0. And if I wanted to connect my dots for that one, I'm not going to use that thick of a line. Let's go back down to here. And so that right there is going to be my f inverse of x. That's my graph point. All right, last one for the day. Page 350, number 40, it's a word problem. They give us a function. They say c is equal to 5/9 times the quantity f minus 32, and hopefully a lot of you guys recognize this particular equation. It converts centigrade or Fahrenheit to centigrade, and so that is, and so where values of f are greater than negative 459.6. I'm assuming that's absolute zero, but I'm a little off on my chemistry. And F is degrees Fahrenheit. I never learned how to spell Fahrenheit. Fahrenheit. And then C is degrees Celsius. That's good enough. All right, so the first thing says, find the inverse of the function c. So this one, yeah, I say we switch x and y, but we're trying to get f by itself, and that's essentially all we're doing here. So for part A, I'm going to multiply both sides by 9/5, and then those 5's cancel, the 9's cancel, and then I'm going to flip it. So I've got f minus 32 equals 9/5 c, and then add 32 to both sides, and I get f equals 9/5 c plus 32, and there's my part A. Okay, and then part B says, what does this inverse function represent? It converts degrees C to degrees F. Part C says, what is the domain of the inverse function? And so the domain of the inverse function is essentially going to be all real numbers, but because the algebra says that, but our Fahrenheit numbers have to be bigger than this. So what they're going to say is they're going to ask us to be C has to be greater than, and the way that we're going to calculate that is we're just going to plug this this number right here into our original function. So I'm going to do that real quick. It was 5/9, and then it was, let's see here, 5/9 times the Fahrenheit, so negative 459.6, negative 459.6 minus 32, and so I get that. Uh-oh, what did I have wrong here? Oh, I hit minus instead of negative. All right, now I think we'll get it. So negative 2, so this is the degree C have to be at negative 2, 73.111 to 73.111 degrees, and I'm assuming that's absolute zero, so it has to be greater than that, but I'm not sure. All right, so part D, it says explain the temperature 22 degrees C. What is the corresponding temperature in degrees Fahrenheit? So basically, I'm just going to go F equals 9/5 times 22 plus 32. I can do that real quick. 9/5 times 22 plus 32 equals 71.6 degrees Fahrenheit. So this is 71.6 degrees F. All right. Well, folks, that is the end. And if you have any questions, again, feel free to, oh, didn't want that. If you have any questions, feel free to use the email that is associated with this address or leave questions in the comment below, and we will see you next time. Goodbye.